All right, so integration by substitution is the hardest type of integration that we have to do. So we've learned a couple rules of integration already, but what ends up happening when we did the chain rule and you did the derivative of the outside function and then you multiplied by the derivative of the inside function, you got a new answer. Well, integration by substitution is to try to undo a chain rule. Now, undoing a chain rule is easy if things look perfect. So this was an example that we had earlier in our notes. We were told that the derivative was this. This was back when we did the chain rule, and you were asked, could you think of the function as it was originally? So in this one, it was really easy because can you see that the 5 has come out in front and there's a 4? So in our original function, we would have something to the 5. In fact, we'd have this 3x squared plus 5x to the 5, because that 5 would come out in front and you'd subtract 1 from the exponent. And then when you did the chain rule, you would multiply by the derivative of the inside. And can you see that highlighted here in yellow is the derivative of this inside function, which I've highlighted in green. And so this would be the original function. Of course, there would be a plus c now, because you could have any constant at the end. Now that was really nice because it was straightforward and easy because the 5 came out perfectly in front. There was a 4 there. We simplified it and had a function. But sometimes we're going to get functions that have been partially simplified. Like they might multiply the 5 times the 6x plus 5 and have 30x plus 25. And it's not going to be as easy to work backwards. So we develop a technique which is called integration by substitution to help us do that. The first thing for using integration by substitution is to be able to recognize when a chain rule has happened. And if that chain rule has happened, what are the parts? So what we're going to do is we're going to take out our highlighters. We are going to highlight a function in yellow and see if its derivative is there, and I'm going to highlight that in green. So what we're looking for is a function inside, because that's your original inside function. So for example, in the first one, I have an x squared minus 7 as an inside function, and I'm going to highlight in green that I notice the derivative is there. Now, what's going to make integration by substitution sometimes difficult is when you're looking for the derivative doesn't have to match up perfectly. In other words, the coefficient could be different. We could still do this question if the green part was a 4x instead of a 2x. Because the yellow part, the derivative of that inside function is 2x. But if you had any multiple of 2x, then you would still have that as a constant out in front and could still work with that function. For the second one, we're looking for an inside function, which the derivative shows up in the equation. Can you see that I have an x squared minus 3x? And the derivative of that is 2x minus 3. So in our chain rule, that yellow part would have been our inside of our function. And when you did the chain rule, you would multiply afterwards by the 2x minus 3. The third one, a little bit trickier to see. Can you see that you have x cubed minus 5x is an inside function. It's in a 1 over x equation. And its derivative is 3x squared minus 5. See any functions and their derivatives apparent in the last one here? Yes. The derivative of tan is secant squared. So then tan would be our inside function, and sure enough, tan is inside of sine. And then we have our derivative here afterwards. This one is missing the dx at the end. What's the derivative of natural log? 1 over x. So here we have our inside function, natural log, and sure enough, our derivative is right there, but it's written as x to the minus 1 instead of 1 over x. What's the derivative of sine? Cos. What's the derivative of cos? Negative sine. So in this question, we have the derivative of sine is cos, and we have both sine and cos there. The derivative of cos is negative sine. Again, we're not worried about the coefficient. So we have to decide which one is the inside function, and then which one is the derivative of the inside function. So in this case, the sine, can you see that sine x is inside of the e to the x function? And so for this one, sine will be our inside function, and the derivative of sine is cos will be our outside function. Do you see anything and its derivative in the seventh one? 3e to the x, the derivative is 3e to the x. So now we've got exactly the same number. I've got to highlight 1 in yellow and 1 in green. So which is the inside function? The 3e to the x. Perfect. You guys are amazing. And which one's the outside afterwards? The 3e to the x. So when looking at this, though, the inside function here will be this one because it's inside of cos. And then we're multiplying by 3e to the x afterwards. For this last one, okay, we've got sine. The derivative of sine is cos. The derivative of cos is sine. So you could think of either way doing the yellow and the green as far as substitution. You have 2x inside. This one is going to have some interesting things because it could happen in various ways. You could say, I see one function and its derivative this way. I see a function and its derivative this way. You might also see an identity or a couple of identities and be able to work with that. So when we get to this last question, there's going to be a couple of different methods that we can use to work with that one. So how does integration by substitution work? Well, if you notice exactly what we've been highlighting, if you notice there's a function inside, and for this, there's just a little typo. This shouldn't be like an x to the power. This should just be a regular x in here. So I don't know if you want to make your x bigger. But what we did before is we said if you see a function inside of another function and you see its derivative present, what we're going to do is we're going to substitute. We're going to substitute, instead of writing the inside function, we're going to write u. So our inside function is going to be u. And instead of writing our outside function, our derivative there with a dx, we're going to write du instead. Now, the reason for this is if you had some function u and you did the derivative and you substituted u is equal to g of x, if you did the derivative of du dx, you would get the derivative as just g prime of x. Because if u is equal to g of x and you take the derivative will be g prime of x. And we do a little bit of notational fancy work here. It doesn't actually make mathematical sense. Can you see on my black arrow what's changed? I moved the dx from the bottom of my derivative to the other side. And then this whole part is my green part that I put in. Mathematically, this works, not because you're allowed to multiply both sides by dx, but we sort of use that as a shortcut, and we're not going to worry about the explanation of fundamental theorem of calculus of why that works, but we're going to just go with it. If you're okay with that? Because technically, this is the derivative, and du dx means one thing. So you can't really take part of it and move it over to the other side. Doesn't mathematically make a lot of sense, but in this case it works, and we're going to just go with it. So, what does this all mean with our questions? And how are we going to use substitution for this? Now, in this case, you can see that we've got our inside function, x squared minus 7, like we highlighted before, and the derivative of it is present right there. And I'm going to highlight the dx with that. We can't work backwards perfectly like our initial example, because normally there would be a number in front and everything would work out nicely, but those numbers in front aren't there. So what we do for substitution is we always let u equal our inside function. And our inside function here is x squared minus 7. Then if we found the derivative of that, and we'll use Leibniz notation, the derivative would be 2x. And so that means in our equation, we can replace the 2x and the dx with du. And again, as far as highlighting goes, that's what I'm going to replace my green with. And this is what, oops, that's not yellow. This is what I'm going to replace my yellow with. So now if I do that substitution, I get the integral of u to the power of 4 du. And this is an integration that we've done before. How do we integrate with our power rule? Add 1 to the exponent, divide by the exponent, plus c. And then once you've done that, you can substitute back to write things in terms of x. So u was x squared plus 7. It's going to be divided by 5 to the power of 5. Minus 7, thank you. Minus 7 plus c, where c belongs to all the real numbers. So what we've done is we've substituted to get it into an easier form that we could use our regular integration rules to integrate, and then wrote and substituted back in the end. So on some of these questions, you might have been able to say, maybe I could see it directly. These are hardest ones to see directly, to go from that answer to this answer, but sometimes people can see that. Where things get tricky is when the numbers in front don't match up nicely. And that's why we use this technique, and we will use this technique a lot. Dawson, question?